talk about, however. We're going to talk about big data. And what is the big deal about big data? So apparently the title was attractive, otherwise you wouldn't have shown up. So big data means a lot of things. Right? So it's a very interesting acronym Sqoop, or new words, catchy product names, etc. But what does it actually mean for us, right? So depending on who you talk to, there are people that think this is purely about size. Actually, I don't believe that that's true. Right? Size is important, but actually if you start to think about it, it's like there are 3 V's or 4 V's actually that determine it's like some of the interesting characteristics of big data. Right? Volume is one of them. But variety and velocity are 2 other key characteristics that people are trying to deal with. Another part is that people associate it with the notion of using massive clusters of commodity hardware. For example, so I have a lot of friends at Facebook. Today, Facebook uses 2,700 nodes, 2,700 nodes, to actually compute over their 20 petabyte storage that they have. And they do that based on really commodity hardware. Right? And that's one of the big trends that we see in the big data world is PCs these days, server PCs even, it's like they're dirt cheap. Right? And what people try to do is like what we tried to do in the past in terms of scaling up massive hardware. It's like we now see that it's much more economically sensible to take a large number of cheap boxes, we call them pizza boxes, and stack them up. And you can see the picture, right? It's like we do like pizza, so and stacking them up, it's like actually makes sense. So big data also means to a lot of people NoSQL. Actually, those two are not really necessarily correlated, and we'll talk about that, why. And I'll make that distinction in a moment. It's like what is key there, but it's like you will find things there is MongoDB and RYAC and CouchDB, but that's we'll talk about that more tomorrow actually. So let's talk about some statistics to sort of see is like where things are going. If you look at some numbers today, and it's like there are so many studies out there that you can pull them from anywhere. One of them that I like because it also sort of gives a trend between the segments that we have inside the market, and I'm sorry these are US numbers, but if we look at the US market, in 2009 it was estimated that we have 1 zettabyte of data online. So that's 1 million petabytes. Now that on itself is interesting, like the amount of digital data that is available that we need to work against. The interesting thing is that we know that the amount of data that is digitally born and that we need to handle is going to increase by a factor of 35 to 40 by the year 2020. Right, that's 7 years from now. And so how do we deal with that? How do we actually go from there? Now, you might say it's like, well, this is a geek talk, right? IT guys, we love to talk about this. But actually, it's like, if you look at a magazine as The Economist, which is not typically something you will read probably, right? It's like that's what your boss reads maybe if he wants to grow up, right? But this is what your CEO or your CFO or your COO reads. And actually, if you go to the latest economical conference that was done at the G12, it's like big data was one of the topics on that agenda in terms of how does the world need to be dealing with this. So it's not just on our mind, it's actually on a lot of people's mind. So why is that? Why are we suddenly so interested? Well, first of all, we generate a lot more data. If you walk around with a smartphone, you're generating a truckload of data by just walking around, if you know it or not. Your provider will track where you are, keep your GPS location. We have sensors in everything. I just installed actually inside my house, it's like a thermostat that has an IP address. So I can log into it and I can remotely control it. It's like if I could project my phone and it would work actually from here, I could show you that I can control my temperature of my house from my phone that way. The other thing is that thing collects a truckload of data. And I can actually see if my wife or kids are in the house because it will automatically turn up the heat. And if it senses there's nobody, it will turn it down. So you don't have to put a clock in it, which is what we've been doing for years, of course. But it's like, I don't live by a clock these days. So this is much more convenient. But it generates a lot of data. Twitter feeds, web clicks, we all know from the past. Now, what we've come to the realization, though, is that we have a lot of data, and we used to have a lot of data, but actually we now come to another realization that that data might be too valuable to actually delete. So what do we mean with that? Right now it's like we collect a lot of data, we don't know how to apply it. What is the exact application for that data? So in normal cases we would actually throw it away. Say, all right, we don't need this. Well, we don't know what to do with it, so we'll leave it. More and more we come to the realization that we actually can use this data later on. And the other part is that there's a lot of data that we need to know now. One of the projects I'm involved with is designing an architecture, for a reference architecture in this case, is how do people deal with sentiment, right? Sentiment data from social networks and incorporate that into their environment. And so that's one of the other aspects that we're looking at. Now, one of the other key parts, of course, is that the cost of storage has been going down dramatically. And today, it's like a terabyte disk. I was just looking it up at Fry's, which is a retailer in the US. It's like a 1 terabyte disk is about $99. That's not a lot of money. Now, is that the most reliable disk? No, but it's like, that's the whole point. We will actually deal with that. So we used to deal with a lot of this data, and if you go to the eBay guys, it's like this, it's like, it's like we've been dealing with large data, 10 petabytes, last time I asked them, on 256 nodes. And they were doing this using a parallel database system. And so a lot of people today refer them as the old guard. Because if you go to the Facebooks of the world, they will tell you it's like, hey, we do it 20 petabytes, 2,700 nodes. Now they have a slightly different profile, so these numbers do not completely compare, but there are some interesting things that I'm weaving through the presentation of things that you need to understand about this architecture. Now Bing itself, if you were wondering there, is like we actually use a massive scale-out technology as well. So Bing today is 150 petabytes, and we have 40,000 nodes, compute nodes inside Bing that we use to actually manage across the world and troll for feeds, etc. So let's drill in on NoSQL actually for a moment. So why the name? Well, so first of all, like a lot of people, and I'm a SQL Server guy, so it's like, NoSQL, it's like, what do you mean? It's like, SQL is a bad language, it's a dead language. What are you telling me here? Alright, and depending on who you talk to, is like this becomes quickly a religious discussion, which is always fun with a beer, and but really it's like, it's not only SQL. What the big, I think, epiphany is that there are more storage solutions than just a relational database, thankfully. Alright, and for those of you who are coming from the developer world, you probably know is like the interesting impedance mismatch between the developer environment and a relational database. If you want to know more about that, I'll talk about that tomorrow. So why did people actually go down the NoSQL route? Well, first of all, they wanted to have more flexibility. They just didn't want to go and model a set of tables and work with a data modeler or a DBA to figure out what their model is. They wanted to drive that from their code. They wanted to drive that in a form that was natural to the application, so a lot of them chose JSON as their data model. they didn't want to cohere to the requirement that they have a schema first. Now they also had other requirements in terms of what is the availability or the consistency that we have. They wanted to do sharding. So they wanted to have information available on multiple nodes, which requires you to ultimately relax consistency models, which flies right into the face of a relational database, because it will say, my first rule is the asset properties. I want to be consistent. Right? So they were willing to trade consistency for availability, for example. They also took this approach, the same approach that a lot of web startups and big companies like Facebook and Google took, and Amazon for the same matter. It's like they wanted to start with low upfront software cost. So they wanted to start with pizza boxes and machines and software that were available. And then most people accused them that they actually never learned anything else than Java or C, which is not true, I know that. But it's like the NoSQL movement is really driven and motivated from a developer's point of view and not from a data storage or data modeling point of view. So a lot of people will ask the questions like, do you really hate SQL or not? Now to me, the most important thing actually that makes NoSQL stand out is the fact that the time to insight into the data between acquiring the data and getting the insight, that is one of the key things. I will show you that actually in the next slide. So how do we work inside a relational world? So in a relational world, it's like we start first with, we know that there is some data, and second step must be derive a schema. Right, you have to go declare some tables, some other pieces, and you're going to create your database, and then you're going to cleanse your data because it's probably not clean or not clean enough to fit into the relational model. You might have some transforms, you load it in, then you have it in your database, and then you can run some queries. So that's the schema first world. Now there's nothing wrong with that, but this takes time to set up. How much time does an average project take? Hours, days, months, years?
Years.
All right, depending on the organization, it's not instant, it's not quick. All right, and the other thing is like, it's not very agile. Being able to change this environment takes a lot of pieces that need to move around at the same time. So what do the NoSQL guys do? Well, when data arrive, they store it. And then they have some applications that will use it. Right? And they use different storage technologies, you will see in a moment. Right? They don't clean the data. They don't ETL it, they don't load it and extract it. Right? And they analyze the data when and where it lands. So what they did is they actually created what people refer to as a schema-later environment. But it gives them a piece of agility to actually work through this. So in order to do this, we actually see two major buckets of NoSQL systems. So we see everything that derives from a key value store. Right, the Mongos, the CouchDBs, the Cassandras, even Windows Azure Table Storage is a NoSQL store. Right? It uses key values to store things. Most of them, as I said, use JSON as an object model for representing the data. Not necessarily as a storage model. Some of them do. Some of them transform it into binary JSON, like MongoDB. But they all have some characteristics around this. A lot of them actually allow you to shard, so spread things over multiple nodes, and they do this based most of the times on hashing. So they hash the key because it's a key value store. So if you have a consistent hashing mechanism, you can figure out it's like which node you'll end up with. And then it's like they retrieve those things based on a key.
What is sharding?
So the question is, so what is sharding? So most database developers would say partitioning. Right? It's the act of like actually distributing your data over multiple nodes. So then there is Hadoop, right? And Hadoop is actually a different category. It's not necessarily a storage system. It is actually two things in once. First of all, it's a distributed execution framework. All right, and then it's a distributed file system underneath there, which allows us to actually store massive amounts of data, right, and do data processing on that data without necessarily using a data model directly, right, because those records or this information is now stored in the distributed file system underneath. So that actually comes to a main part of a conclusion that says hey, there are now two sorts of reality, and they live side by side if we like it or not. Right, we have a bunch of structured data, and we have a growing amount of unstructured data that comes in with a volume that is unprecedented that we need to deal with. Right, and right now is we would categorize that as the structured data lives inside our relational database world. Unstructured lives in NoSQL. Right. The key differences are do we know, when do we know the schema? Did we define that schema? How do we deal with consistency and atomicity? Do we have transactions? Some of these systems simply don't care about transactions. What language do we use to actually go about it? And how do we actually move between the states? When do we load, etc.? So is this really a paradigm shift? Right? Is the world dramatically changing from what we know? Well, I do believe that the world has changed. Right? At least we do. Relational database systems are no longer the Swiss Army knife of the IT industry. Right? For the longest time, we have been trying to retrofit the world into a relational database. Not sure about you, but I've seen my fair share of projects that weren't really successful. So the SQL guys amongst us, we also have to accept that this is actually reality. There is these two different worlds out there that we need to incorporate. But this is definitely not a paradigm shift, because that would mean that one of them would move away and no longer exist. Because relational database systems will have their role, especially in dominant transaction processing, because there are types of workloads. Financial transactions, for example, where an eventual consistency model would be the nightmare of your auditor. Now, maybe this is a new laundering scheme for KPMG, but I don't think that this is really what people would want to build their business on if it's about financial transactions. So, conclusion is, many businesses will end up in two camps. So the rest of this talk, therefore, I'm going to focus on Hadoop and its ecosystem, because we're going to work in two worlds. And so one of the things that we do is we'll talk about in a moment, is what Microsoft is going to do with regards to Hadoop. So what is Hadoop? Well, in order to answer that question, we actually have to go back to 2003. So in 2003, Google started, and when Google started, they were a small company, they didn't have money, but they have massive amounts of data. They had all these click streams that they had to go through. And so what did they do? They actually created two big assets. MapReduce, in this slide we refer to as MR, and the Google file system, a distributed file system, GFS. So what that allowed them to do is use pizza boxes, cheap hardware, and as you may know, is these days they actually build their own hardware, right, to get the best energy specs and cost of the SKUs down. So they build it on just common off-the-shelf hardware. They stack them together in thousands of nodes, and they were creating a high-tolerance environment. Right. And they needed a way to program against these thousands of nodes in a very simplistic way, which would also allow them for that program to be highly tolerant to failure. So these two components were then picked up by Hadoop in 2006 and turned into what became Hadoop. So Hadoop actually is two big things. HDFS, which is the Hadoop Distributed File System, and MapReduce, which has the same name as we had in Google. That's the processing. So what does Hadoop actually deliver to us? So first of all, it provides us with this scalable, high fault tolerance environment. All right. Where we have the ability to analyze data in a way that will allow this to be done in a massive parallel structure without having to be cleansed and modeled. All right. We use MapReduce as a programming framework to actually do this, so somebody can write those programs in a reasonable, sensible way. All right. We do this at a very low cost up front. This is not talking about total cost of ownership at the end, right? Because maintaining massive amounts of machines is still costly. Right? It's not free to have like big 40,000 nodes, even though they're common off-the-shelf hardware boxes. Right? But definitely your upfront cost is lower. And it enables one key scenario. Right. What do? They analyze data. So reviewing the market for data warehousing, or if that's what you're actually going after, this is one very interesting trend. So what is inside the Hadoop ecosystem? So we saw HDFS, our fault-tolerant file system. On top of that, we layer MapReduce, which is our framework for writing these applications. Then we have Hive and Pig. Great names, right? Which is a declarative language that sits on top of the MapReduce framework. We'll talk about that more. We have Sqoop, which is actually a way for moving data between HDFS and relational database systems. And then there is a whole ecosystem around this. And don't confuse Afro with the television guys in the Netherlands here. They have nothing to do with that. These guys can actually serialize themselves. So what does this all have to do with Microsoft? Well, on October 12th last year, we announced that Microsoft is actually going to embrace Hadoop and provide a Hadoop distribution. So what we're doing right now, and this is one of the things I worked on the last 1.5 years before I picked up my new job, is that we're actually delivering two things. We're delivering a Hadoop distribution that runs on Windows, which will be contributed back to the Apache Foundation. And we're standing up a hosted Hadoop environment inside Windows Azure. We're building some ODBC drivers and add-ins, so you can actually glue this in to the existing product set that we have, like Excel and Power Pivot, reporting services, BI stack. Because at the end of the day, Hadoop is a framework for processing data. That doesn't give you it into the hands of the user yet, right? You need to walk the last mile to actually finish your value proposition of your environment. And then we have some connectors that allows you to connect from within Hadoop to SQL Server and SQL Server Parallel Data Warehouse, or PDW as we call it internally. We do this in collaboration with Hortonworks, which is the company that started from Yahoo, right, and now hosts Hadoop. So, before we go on, I want to give you a sneak preview of where we are actually with regards to hosting this inside Azure. So what you will see here is like, and some of that will start to make sense as we go on. It's like, so setting up a Hadoop environment in your own world, it's not that hard, right? It's like I actually have an environment on my notebook these days, right? Because HDFS is just an abstraction on top of things. But it's like, if you want to try things out, it's definitely a lot easier to actually do this in Azure. And if I remember my password, that would probably help me. All right. So we're logged in. So right now this is at CTP level. All right. You see tiles everywhere. No comments on that. All right. So this is my cluster. It's the Datadude cloudapp.net cluster. Right now I have 8 nodes. I can bump that up to 32 nodes if I want to in the trial. I can create my cluster and release it. And so right now it's like the main thing that I have is like, so I have an interactive environment where I can go through JavaScript, where I can go through my environment, right, and see where I am and move all the things around. I can push Hive queries to my environment if I want to. Right now I don't have any Hive tables defined. I can go through, I see here my jobs that have been running, for example, my terabyte sort, right, that has been running on my system. And so right now I can push all these things, and it's like once we've gone through Hadoop, it's like some of these things will hopefully start to make sense. Now the key thing that I show you this right now is that this will allow you to take what we're talking about, the rest of this presentation, actually go to Azure and try it on your own. All right, and so we'll see that from there. So what are we going to talk about from here? So let's talk about the underpinning. So I'm a strong believer in learning people how to fish instead of telling them where the food is. All right, that way it's like you see and understand the ramifications of choice. All right, because there's a lot of hype about this, and there's a lot of goodness, but everything comes with trade-offs. And what I would like you to understand after you leave this presentation is where the trade-offs are. All right, so you have an idea about, it's like if somebody says like, well, we should do this in Hadoop, or it's like we should take MapReduce or use HBase, or what those things mean to you from a technical point of view. So we're going to talk about is like how the file system actually is built up, what that means, how MapReduce sits on top of this, and how all the other components fit into this picture. So let's get going. So first of all, the Hadoop file system. So what they did actually is pretty clever. All right, so the HDFS, first of all, is the underpinnings of the entire Hadoop system. So you always run HDFS. Otherwise, you can't run Hadoop right now. So it starts off with a bunch of design principles which are key to how Hadoop works. First of all, again, it's built around this notion that you use pizza boxes. That you use massive amounts of cheap boxes that you stitch together. So when you say that, it's like, what is it that you think? Like, wow, I have one of those cheap boxes and they constantly fail. Yes, welcome to the cloud. All right? So one of the paradigms in the cloud is that you should expect failure. Things will fail. It's not a matter if, it's a matter of when. So you should always design your system, not just HDFS kind of systems, but everything you do in the cloud. If you're building a cloud app, you should assume failure. All right? Paradigm shift number one. It's like I took my team, small anecdote. So before this gig, it's like I used to work in the directory team, which is part of Windows, as you might know, Windows Server. And my task was to take them and move the directory from what you know, Active Directory on-premise using a Jet database into the cloud. That was my role. So I had to take a bunch of Windows developers. And if you think Windows, it's like you probably think long cycles, and yes, that's true. So it's a year planning, a year coding, and a year cleaning up. That's their mental mindset. And those time slots might get bigger. Sort of give you the picture. How do you get those people to move to the cloud? Well, first they wanted to write specs for a year. It's like, no, we're not going to do that. And second of all, it's like they wanted to write the specs because they wanted to have everything perfect. It's like, no, you need to start learning, right? And how do you, if you build up services in the cloud, it's like you should assume that they fail. But you cannot go back to the user and ask them for a repro. Because their session is gone. So your infrastructure needs to be zero repro. It's like you spend much more time on logging and diagnostics than anywhere else. Right? All these things are important. Right? So they started with all these principles inside HDFS and said, like, we're going to assume failure. It's just a given. Right? And you will see this throughout their whole system. Right? And So they organized this in a very traditional way using a hierarchical directory structure, as you will see. And they wrote this all actually in Java, so it's highly portable.